Good afternoon. I'm Sunho and I'm from KAIST. Today I will talk about the unified memory protection with multi-granular MAC and integrity tree for heterogeneous processor. This work was conducted by KAIST and Georgia Tech. According to the recent trend of AI processor, the specialized high-performance devices such as GPU and NPU have emerged and integrated within a single chip. As AI systems use the secret machine learning models and the personal data, the importance of security increases. Unfortunately, there are lots of security attacks that can compromise the data confidentiality and integrity. Therefore, the memory protection for heterogeneous processor is necessary. The prior existing memory protection schemes are tailored to the specific memory access pattern. For example, the common counter is used only for the GPU medium-grained access pattern. And the study of the software-based counters are only for the NPU software-detected access pattern. However, the heterogeneous processor have a diverse access pattern from multiple processing unit. It makes the prior studies inapplicable. Therefore, we focus on the unified memory protection for our processing unit, our access pattern. However, to support the unified memory protection, the integrity tree optimization is necessary. However, the prior study does not bypass the integrity tree optimization, restricting their security boundary to the specific access pattern. This study constructs a unified memory protection scheme with integrity tree optimization for heterogeneous processor. The widely used memory protection scheme is the counter mode memory protection. Each ciphertext is paired with a single counters and a single MAC. A counter which represents the number of write back is stored with the ciphertext and used for data encryption. And the MAC, which represents the hash value of the ciphertext, is used for integrity protections. Counters are structured in a counter integrity tree, and counter integrity tree is used for replay attack protection. The replay attack protection is supported by the recursive validation procedure. Since the memory protection overhead is closely related to the amount of the loaded security metadata, the size of the ciphertext called the security granularity is important. And also to reduce the integrity tree validation procedure, the height of the integrity tree is also important. In a heterogeneous processor, the conventional fine-grained and full integrity tree-based memory protection causes 34% of performance delay with 29% of data traffic increment in a heterogeneous processor. Therefore, this conventional method is not well fitted for the heterogeneous processor. So there are many significant overheads caused by the conventional way. So how the heterogeneous processor reduce this significant delay? To identify the unique characteristic of the heterogeneous processor, we measure the access granularity. In this study, we define the memory chunk as the consecutive access to fine-grained memory blocks. First of all, the finest 64-byte chunks are mainly shown in CPU execution, and in a GPU cases, there are lots of medium-grained access chunks. And meanwhile, there are lots of coarse-grained access in the NPU execution. Based on this observation, matching the security granularity to the access granularity significantly reduced the amount of the loaded security metadata. It means using a single pair of the security metadata per memory access chunk reduce the memory protection overhead and improve the performance. To handle this heterogeneous memory access pattern, multi-granular MACs and multi-granular counters are necessary. The conventional fine-grained MAC have large overhead. In a conventional fine-grained MAC, all data blocks have their own MAC. So the conventional fine-grained MAC fetch a large amount of the MACs, and it caused the high overhead. In a prior study of the dual granular MACs support two types of the granularity. So this dual granular MAC partially reduced the memory protection overhead. However, to improve this partial improvement, we proposed the multi-granular MAC. Our multi-granular MAC significantly reduced the amount of the loaded MACs and its fetching overhead. By managing the security granularity, we can support the multi-granular MAC, and this multi-granular MAC can improve the performance. So it is easily support the multi-granular MAC. But what about the counter? To support the multi-granular counter, there are several prior studies to support the multi-granular counter. However, this study bypassed the integrity tree optimization under specific condition. In case of the common counter used the kernel level updated storage with limited capacity for coarse granular counter. If the required coarse granular counter does not exist in the limited storage, the coarse granularity cannot be supported. Therefore, the common counter is only for the GPU kernel level execution. In other cases, the software-based study used the software-managed storage for coarse granular counter. Under the software control, it removed the integrity tree validation procedure. So this software-managed studies is only for the software-controlled workloads such as the machine learning. In summary, these studies do not handle the integrity tree optimization. However, for diverse access pattern in the heterogeneous processor, supporting the multi-granularity on the integrity tree is necessary. So let's assume the conventional fine-grained integrity tree. The conventional fine-grained integrity tree fetch the large amount of the counters, causing high overhead. It also has a long integrity validation path. To solve this problem, we proposed the multi-granular integrity tree. Our integrity tree maintains the counters with diverse varying granularity in the different level of the integrity tree. Our multi-granularity integrity tree significantly reduced the amount of the loaded counters and its fetching overhead. Also, it shortened the integrity tree validation path, further reduced the memory protection overhead. From this analysis, we proposed the multi-granular MAC tree. It supports the dynamic granularity management procedure. From the conventional fine and fixed granular MAC tree, our multi-granular MAC entry reduced the amount of the security metadata. For this transformation, merging the counters and MACs and pruning the integrity tree is necessary. To support the multi-granular MAC entry, we should consider how to dynamically detect the granularity and how to dynamically switch the granularity. Let's assume the granularity scale-up scenario. For granularity detection, the access tracker records the access pattern using per cache line access bit. Due to the coarse granular accesses in the scale-up scenario, the consecutive access bits are set. After that, when the access tracker entries are evicted, the granularity detection engine computes the new granularity based on the recorded access pattern. Then the new computed granularity is updated on the granularity table. Then the granularity switching requests are detected. The granularity scale switching engine fetch the additional data. After fetching, the switching engine computes the new MAC and counter based on the old MAC and counter. After computing, the data blocks are re-encrypted and the MAC and counters are replaced. Finally, the unnecessary integrity tree nodes are pruned. In this process, we hide the most of the switching overhead by the lazy switching procedure. For more details of the lazy switching, please refer to our paper. Now I will explain the evaluation setup of our study. We use the combination of 3 different simulators, Cheongsim, MGPusim, and MMPusim for heterogeneous simulation. We follow the NVIDIA Orin configuration. We use 14 workloads with diverse access pattern and diverse traffic intensity. Now I will explain the evaluation result about the average normalized execution time of heterogeneous processor. It is the average value of the normalized execution time of 1 CPU, 1 GPU, and 2 MPUs. Our multi-granular MAC entry get 14% of performance improvement with 11% of data traffic reduction compared to the conventional fixed and fine-grained MAC entry. By combining with the prior subtree optimization, we finally achieved 21% of performance improvement. In a breakdown, 7% improvement comes from the multi-granular counter, and another 7% from multi-granular MAC, and the other 7% from the prior orthogonal subtree optimization scheme. Now I will explain the evaluation result about the normalized execution time of each processing unit. While the MPU only achieved 10% of performance improvement, CPU and GPU get 24 and 23% of performance improvement. It is because the traffic block caused by the MPU are released in our design. There are more detailed design explanation and detailed evaluation analysis in our paper. Please refer to our paper. In conclusion, we propose the unified memory protection for heterogeneous processor. In this process, we use the multi-granular MAC entry. Thanks to multi-granular MAC entry, we solved the challenges of handling the diverse access pattern, and we finally get 14% of improvement, and by combining with the prior subtree optimization scheme, we finally achieved 21% of performance improvement. Thank you for listening to my presentation.